been a PhD student in my group since I think fall 2017. He's been a wonderful PhD student to work with, and it's been really a pleasure to have him in our group. He's been somebody who selflessly thinks about others, helps others all the time, and while doing so, has also managed to be an extremely prolific graduate student. We were looking and counting up his publications, and I think he's at 15 publications. Some of those are under submission right now and or under review, but 5 of those are first authored with another submitted. And then a point of pride of his is that he's actually mentored undergraduates, been the primary mentor on at least 3 of those papers. So extremely productive student. In addition to his research, he's been able to help the materials informatics community, which is really still in its infancy and it's growing now, but he's been a major player in helping shape and form it to have best practices. He's been the primary instructor for 3 different workshops that we've held, one here at Utah, one at Houston, and one for the UCSB materials department. I just found out last night that a paper that he is one of the lead authors on, published in Chemistry of Materials on the best practices for materials informatics, was just found to be the top 20 articles in the year 2020 for a great journal like Chemistry of Materials. So I think his work stands for itself. I could go on, I haven't even mentioned the great talks he's given. Maybe I'll just give one more shout out, is that the North American Materials Colloquium Seminar Series is a prestigious seminar series you have to apply to. We only get to nominate 1 student, and they actually selected Ka'ai to be a speaker this spring. So I think that's February 12th, I believe, is when he's going to give that talk. So I could go on. Ka'ai's been a brilliant student. He's done some groundbreaking work, and I'm excited to have him share it with you all today. So Ka'ai, without further ado, let's have you tell us about your work.
Thank you so much, Taylor. So I work in the area of materials informatics, which is the application of machine learning techniques to material science data and problems. And kind of the outline of how we're going to go through this today is I'm going to just choose some papers that I thought highlighted some fun things that I did research on and that I published in the field. And then kind of, say why I think those papers, really contributed something nice and, were a good reflection on my time in the PhD. So before I talk about those, I want to just thank people. Of course, first I want to thank my family, especially my mom and my dad, who recently passed away. I just want to, they always support me. They've been really great during the PhD and, really understanding of the, the kind of effort it takes to do something like this. And then I also want to thank my wife, who's sort of struggled through school with me these last 4 years, who's been doing medical school. I'm super proud of her, and I think she's super proud of me. I know she is. And then I want to thank the people who are directly involved with this research. First is Dr. Taylor Sparks himself. He's been an incredible advisor, an incredible friend, and just a good person all around. He's probably the favorite teacher in the department as well, which speaks, volumes towards who he is as a person. And then a couple colleagues I've worked with. I think you guys can see my screen just fine. Here in the middle is Dr. Jake Gracer, who recently got his PhD and who I had the pleasure of working with for about 3 years. And he does like experimental synthesis and characterization of materials. And so he was just a great, resource and friend. We'd bounce ideas about, what machine learning should do for material scientists. We'd bounce ideas about the latest games we've been playing. Just an absolute pleasure to work with. And then my colleague, Anthony, from across the Atlantic, he's in Germany right now. And he's currently also working on his PhD, and he's been a part of some of my favorite publications. He really helps out a lot in the areas where I'm maybe not quite as strong. He can really take a project and push it to perfection. And so we've been a really great team together, and I appreciate working with him, almost every day. And then last, there's a special shout out to my undergraduate, Ryan, who is now a PhD in psychology at the University of Utah. And Ryan's just a great guy, a great brain, and helped me a lot with, understanding some of the intricacies of neural networks. And, he does a lot of this stuff for fun, which is cool and shows his own drive. Then the last thing is I just want to thank the National Science Foundation, because I believe I'm funded by them. And I mean, it's great to have a government organization who's invested in, minds for the future and research in science. All righty, now that we've talked about a lot of the things that have made this possible, let's talk about some of the research I've worked on. So this is the paper. I didn't know it was like a good, like that great of a paper. I knew a few researchers had, thanked me and had talked to Anthony, who is the primary author on this one, and appreciated us writing it. But what this paper is, Machine Learning for Material Scientists, an introductory guide towards best practices, is really just our attempt to try to bridge the gap that exists between the world of computer science and the world of material science. And in this paper, we talk a little bit about the basics of machine learning, some of the principles involved with handling your data and how you should really think about these problems. And then we step over and we talk about the data that you find in material scientists and like the kind of problems material scientists might be interested in and the solutions people have worked on so far to kind of solve these. So I'm going to use this paper sort of as a scaffolding for us to just kind of get a good brief introduction into both of these areas so that I can talk about the remainder of the papers that I've worked on. And so to do that, we're first going to talk about just kind of machine learning in a sort of vague and nebulous way. But essentially, the process of machine learning is when you have data, we're going to say there's some representation of your data, X, and some target associated with that representation. Now we're going to talk about a thin slice of machine learning called supervised machine learning, and just sort of pretend the other stuff doesn't exist for now. But given data and its representation, we want to try to do something special with our computer. We want to build a model that reflects what's going on in reality. So machine learning's job is to find this function f, which given an input x, returns an estimation of your target value. So down here, I've written f of x equals y prime, which is our estimate. And so really, ultimately, you have a computer try to reduce the error between your estimation and the true target value until you have some function that you hope approximates reality. So to do this, the way you go about this is you use different machine learning algorithms. Now I'm going to talk briefly about a couple of these. The nearest neighbor algorithm is probably the most simple approach you could have. You think of the representations of your data. Let's say I have a bunch of labeled data. I have the x's and their targets y, and I get a new piece of data coming in from some stream outside. Well, I can ask, what's the target or my estimation of the target that I should assign to this new piece of data? Nearest neighbor approach says, look at its representation x, see what it's closest to in the data you already have, and assign it that same label. Pretty simple. There's some clever things you can do with it, but straightforward, probably easy to understand. Now, linear regression is maybe a little more complex without showing a bunch of figures and some math, but it's not too bad. If you've ever opened up an Excel sheet and plotted your data and fit a line through it, you've probably done a linear regression. In junior high, we called it y equals mx plus b. And linear regression is the process of finding that value m, the slope of your line, and the bias, b. With the caveat that in machine learning, typically there's more than just one value x. There's an x1, an x2, an x3, an x4, really to extremely high dimensions sometimes. And so linear regression in machine learning is a process of fitting a line through your data, but in these really high dimensions. The next one is a decision tree method. And I think most people have seen this little graphic. It says should it move? If the answer is yes, but it doesn't, you use WD-40. If the answer is yes, but it does, then you don't have to do anything. Then you could say well, should it move? If the answer is no, and it doesn't, you use duct tape, or you know what I mean? So these are what we call decision trees, essentially little trees where you can take information and propagate your data through it to get to a node that has what you want at the end. Again, machine learning's job is to build these trees, given data that comes in with some representation and some target. And the last thing that's worth mentioning is neural networks. And these are definitely worth mentioning because they sort of represent the state of the art in most fields that use machine learning. And neural networks conceptually can kind of be thought of as linear regressions that have been just stacked on top of each other with the addition of what we call a nonlinearity. And that makes it so it breaks some mathematical properties that allow it to learn essentially anything. But there's some trade-offs with how complex you want your model to be and how close you want it to match reality. Well, given the types of machine learning that we can do, it's important once we start considering these approaches to think of the types of data we're going to see in material science. And I'm going to propose there's three common types that you encounter when you do materials informatics. The first is what we call computational data. And that's essentially a computer tries to simulate physics, and it gives you the output, its calculation of what the answer should be if it simulated physics correctly, if it had good enough approximations. The next data is characterization. And again, Dr. Jake Gracers, who I look to when I think of this, that's someone in a lab. They put all the chemicals together, they bake it, they take it out, they press it, whatever you're going to do to your stuff, you grind it up, you measure it in different machines, you determine, well, you characterize the material so you can determine its physical properties or get a close approximation to the true physical properties. And then the last is like imaging. So maybe you went through all the effort of making something. Well, you can take it, you can look at it under a microscope. You can use an SEM or a TEM, which are super high powered microscopes. And you can look at stuff like crystal grain direction, grain growth, microstructure. Well, all of these data sources are what we want to be learning on. And so if we need to learn on these, we need to represent them. And so we have to think about what data we have coming in material science. We can easily have the chemical composition, probably the most simple. You know what you put in there when you made it, or you know when you simulated it, what atoms you put in what spaces. Well, there might be synthesis steps if you actually did make this thing. What was the ramp rate on your furnace? What was the temperature? Was it in oxygen? Was it in nitrogen? Did you have like sacrificial powders in there? All of this might be important in your machine learning process. So you have to be able to represent that to your computer. Another thing is crystal structure. When it comes to computational data, you need to give the computer an input, and typically that's in the form of like a CIF file, which would have the location of all of the atoms relative to each other. Turns out, if you have that information, and if you can give it to a computer in a reasonable way, I think like graphs in the mathematical sense, then your computer can do a better job learning it than it otherwise would without that information. And if you do have images, well, there's lots of ways of characterizing the microstructure. You could use a simple convolutional neural network. You could do sort of a bag of patterns or a bag of images, or you could just apply handcrafted filters and try to summarize it in some way like that. But regardless, once we have our data, the process is to make that big X that represents the data to our machine learning algorithm. But when we represent it, we also need the target associated with it. And there's two tasks we typically do here. One is called regression, which is producing a real numbered value. The other is called classification, which produces a label. So on the regression end, we might be talking about like mechanical properties of a material. The bulk modulus, the shear modulus, essentially how hard is it to squeeze and how resistant is it to like shearing, or like thermal conductivity. These are all numerical values associated with a material, something you can measure in a lab. On the other hand, classification is easy to think of. If you had like a dinner plate and you looked at all the foods on your dinner plate, you could think, well, given the food pyramid, where do I put that food? What class does it belong to? And so that might be asking whether or not something has a band gap, whether it's a metal or not. It might be asking whether or not something can form at all. Or you might be classifying a chemical composition into likely crystal structures that it could form, given the chemistry and the elements involved. And so with this paper, essentially what we did is we established, well, what's the problem statement? Where are we working in this field, and how do we move forward? And so this next paper, I'm going to look at some applications of machine learning to materials data. What we have here is machine learning prediction of heat capacity for solid inorganics. So a solid inorganic material is essentially, it forms a crystal, it's made of inorganic elements. And what we did here is we went to the NIST JANAF tables. This is a government agency whose job it is to get good data and host it for people, essentially. I mean, they do a lot more than that. But that's what they did for us. And we got a bunch of chemical data, and we asked, can machine learning predict heat capacity at least as well as best practice approaches? So at room temperature, what people usually do is they use the Newman-Kopp approach. This is best practice. Everyone sort of accepts it as good enough for a publication. And what this is if you have a chemical composition, let's take Al2O3, you have 2 aluminum, 3 oxygen. Your job is to try to predict what its heat capacity is going to be at room temperature. So this method, they say, well, all you do is you take the heat capacity for 2 aluminums, the heat capacity for 3 oxygens, and you add them together. And when you do that, you get a good estimate on what your heat capacity should be. So this figure sort of summarizes, says predicted CP. This is the Newman-Kopp prediction of what heat capacity could be. Here on the x-axis is the true heat capacity, that's been measured and characterized by a national lab or something. And what we see here is that 45-degree line would be perfect predictions, and the Newman-Kopp method falls fairly close to that 45-degree line. And right now people say it's good enough. Well, on the right was us asking, well, simply can machine learning do better? And if you look at the data and you look at that 45-degree line, you can see indeed it seems to be more closely correlated to reality when we do this. Now, this is a relatively simple model. It's a linear regression. You're just trying to fit a line with the data we had. But we did something a little more special than the Newman-Kopp method. We didn't just include the elements' heat capacities and add them up. We included other element properties, things like what column they are on from the periodic table, their atomic weight, like the number of valence electrons, etc. These are just physical properties associated with each element that gives us a better intuition to their chemical behavior. And when we fit our model on this, we get improved results upon the Newman-Kopp method. Well, this is at room temperature, and it's a relatively easy problem. Turns out predicting heat capacity at elevated temperatures is not so easy. And what people currently do is either the cation anion contributions method shown here, or like a mixed oxide approach. Think Newman-Kopp, but with parts, both like bigger parts of the composition. Well, you can see clearly that the results aren't nearly as tight to that 45-degree line. And there's this behavior, if you look carefully, where it starts pretty darn good, and then it sort of like veers off. And the reason it veers off is because this data is fit to a power series, this little equation in the bottom right. And there's that temperature squared term there, which kind of can hurt us when you're outside the prescribed temperature range. And so you could say, well, let's just not go outside it. And that would be totally valid, except for this is all real data. This is all data taken from the NIST-JANF tables. And a considerable amount of that real data is outside of those ranges. So there's obviously problems with this approach. And this is where we thought machine learning might be able to help a little more. And indeed, when we looked at it, we saw that we can create a tool that is a little bit more robust to temperature because it isn't restricted by this stringent fit to a power series, that mathematical function. And indeed, at those higher temperatures, it does significantly better. And so now engineers can go in and get fairly accurate predictions of heat capacity, but they don't just have to say, well, if it's above room temperature, we're kind of out of luck. They can now say, well, if it's within the prescribed temperature ranges with the cation anion approach, and if we have the right cation anion contribution or combinations, then we can use this method here on the left. If not, we have a fairly robust method here on the right. And so this work was really just pleasing because it shows a great way of combining current best practices with the up and coming change of perspective towards materials informatics. So our next work then asked, well, if we can do a good model of heat capacity, what other materials properties can we do good models on? And we looked around and we saw an interesting property people had been predicting, the band gap. Now, the band gap of material is fairly useful and it's fairly challenging because you can't calculate it with high accuracy. So there's essentially two types of data that exist. Here on the left, the blue and red, this is computational data. So we simulated physics and we tried to determine what the band gap of a material might be, given the atoms in that material and their relative locations to each other. Well, these two light blue data sets on the right, this is someone going in and measuring experimentally what band gap values were for different chemical compositions. And we saw that people either train a model on the left or on the right. So a model for computational predictions or for experimental predictions. The thing you can't do is mix them because computational band gap values, they kind of look close to reality. They're slightly correlated, but they're kind of really wrong at the same time. So our question was, well, if we want the better predictions, the experimental predictions, the ones that are closer to reality, how do we get them? And can we use all of that extra computational information without actually having to compute DFT for all of them, for any arbitrary composition, and then without having to try to like directly learn exactly how DFT correlates to reality? And the answer was pretty obvious once we thought about it. Well, let's train two models, one on the DFT data, one on the experimental data. And then let's have a model on top of that. So another machine learning algorithm learning from what DFT looks like and from what experiment looks like to synthesize a final prediction that sort of bridges the gap. It takes computational information, it takes experimental information, and it refines the best possible prediction. Well, for that to work, our prediction of computational data has to be at least somewhat useful. And so we looked at it. Here, what I'm showing on the left is, again, one of those parity plots, they're called, where we have the prediction on the y-axis and the actual value on the x-axis. And this is what our model generates when it's been trained to predict bandgap. And you'll see these light blue, these are the experimental data. They're fairly tight to that 45-degree line, a little bit to the left, a little bit to the right. Well, this figure here over on the right-hand side, that red peak and that yellow peak, those are what we call residual plots. And they essentially say how wrong is your prediction. So if you were 0, you're not wrong at all. If you had a single peak at that 0 mark, you have a great model. On this hand, when you compare DFT computed values, so the actual output of a DFT computation, that is simulating reality, to experimental values, this red residual plot shows how incorrect is DFT from reality. And then when you compare our machine learning model that predicts the DFT values to reality, you can ask how wrong is our DFT prediction relative to reality. And we looked at these two and we realized they're essentially the same errors. And when we put them on top of each other, we thought, okay, well, a machine learning model trained on the computed bandgap values is probably just as good, or maybe slightly worse than a model that was given the bandgap values directly. So this should work. And so what we did is we tried it out. And indeed, what we saw were great results. Here on the y-axis is the error, so how bad your model is. Higher is worse. And on the x-axis is the number of data points the model has for training. And more data is almost always better. And what we saw is if you just train on experiment, that is, this SVR model stands for support vector regression, a type of machine learning algorithm. If you just train on experiment, when you have very few data points, you're essentially guessing because you don't really see patterns. And as you get more data, you get better and better and better, just like you should. But if you start with all of the information contained in DFT databases, and your model is only trying to learn the difference between DFT and experiment, you can have 10 data points and do better than you can without that DFT information at 120 data points. And so this was a great work because it showed not only good ways of bridging data that can't otherwise be thrown together for model training, but it also showed that if you're clever about where you get your data sources, you don't need thousands of data points when it comes to training. You can kind of put various models together and get the results you might expect and want from a machine learning model. And so at the end of the day, we improved upon this property and we showed some cool techniques you could use and probably take to other properties, ones with similar computed values. Well, when we looked at this, we saw that there were huge amounts of data for huge amounts of computational data. People have been doing a lot of material simulations recently. And this led to a question, and it's, do we need to incorporate a lot of materials physics when we learn these things? And this is a natural question because if you look at image processing, we started by developing very specific algorithms for very specific image types. We might have applied like filters across those that were handcrafted. We might have done like bag of texture techniques. Well, eventually what ended up happening is neural networks came in, specifically convolutional neural networks. And they said, look, we don't need any type of like domain knowledge. What we need is data. And if we have enough data, we can learn any type of filter you might come up with, but we'll learn the better version of it. And indeed, we've seen that happen. And neural networks are essentially the only thing you want to use when it comes to image processing. Asterisk, I'm sure there's examples of that's not true. But that's not just true of that. Natural language processing, same thing happened. Instead of bag of word techniques or word vectors, once the transformer hit the scene, everything changed. And now we have natural language models that people thought were never possible. And that, again, is purely data driven. It uses a few ideas that come from domain experts, but it doesn't use vocabulary. It doesn't use the meaning and definitions of words to understand things. And so then we asked, do we need that physics, right? Let's come here and say, at what point do we need to not worry about handcrafting features for our data that has all these baked in element properties? Well, to talk about that, I'm just going to briefly talk about what you would typically do when you have small amounts of data. You would take your chemistry. Here I'm showing N2PT1. And so for nitrogen, you have element properties associated with it. I kind of talked about these before. Things like the atomic weight, the atomic number, the column of the periodic table, etc. Just a way of describing that element. Then you have platinum. It's same element properties, but they're going to be different values. And to describe this composition as a whole, you use a single vector. So a bunch of numbers concatenated together. So for this compound, we might take the mean of the element properties, the range of the element properties, and the variance of the element properties. Then the question becomes, well, which element properties do we need? How many of them do we need? Do we need specific element properties for specific learning problems? All of these considerations. And so we looked at that, and we looked at a bunch of different things people have been working on, different ways of generating this vector to represent a composition. And we asked, how does that compare to a vector that simply says, is the atom there, and at what fractional amount? And so we call that fractional here in this figure. So on the left, what you're looking at is the improvement, this is the y-axis, compared to the fractional representation. That is, how much do we gain from incorporating physics into our representation for the model to learn from, relative to the number of training data points. And we think here, as data gets bigger, we expect domain-driven information to be less and less useful because you can learn it directly from the data. And we see this trend is true. So Anton, who's here, has his version of this called the Oleanic vector. And it's great. You can see it's winning. But that's at about 100 data points. It crushes things. It's about 25% better. And as we go, we hit about 1,000 data points and we see things start to converge. And we get to 10,000 data points and we see that we no longer really need any element properties to do as good of a prediction. And then here on the right-hand side, I'm showing the same thing, but instead of the average improvement, we have the R2 score, how close it was to the 45-degree line. This is just a number that tells us that value. And again, we see the same pattern. So we saw this and we kind of thought we answered the question, but then we had one thought also lingering in the back of our heads. Sometimes you don't have all of the elements in your training set. So when you're training your machine learning model, when it's learning how to build that function to represent reality, it might never see tungsten. It might never see carbon. What happens in that situation when it never saw it and you bring it in? And this is where the domain expertise is still valuable to us. We can see that here on this figure. This represents, if you remove any of these elements, how well does your model do when it's tested on compounds with these elements in it? And let's just go ahead and look at tungsten. This is the W down here. We see it's about, when we use Oleanic features, when we have physics built in, tungsten's error is about 60. Well, when we don't use features, this is random information. So essentially, it's a unique vector that means nothing physically to represent each atom. We see that tungsten, because it doesn't look like its neighbors, it does a very poor job of being predicted when it comes to bulk modulus. And so in this paper, we ultimately made the conclusion, yeah, if you have a good representation of all of the elements, and if you have a ton of data, and if you're gonna do learning on that data, you don't necessarily need to use these features that people have been working on. You can use them, and it doesn't really hurt to use them, but you definitely shouldn't spend way too much time trying to engineer your own. It's probably better to get more data and to look at the data you have and make it better. And we'll talk about a situation where I found a bunch of errors in data, and my next project will be to make that better. Well, finally, once we've sort of looked at all of that, we wanted to ask, when it comes to extraordinary materials, can we find them using machine learning? And so what I call an extraordinary material, in this case, is the top 1% of any materials property. So the y-axis is the number of materials in the data set. The x-axis is materials with that value. And you see most things are far below 300 GPa in terms of their bulk modulus. Well, what we did is we asked, if we want to see this question answered, how do we set up the data such that we can answer it in a reasonable way? So we took those extraordinary data and we just removed them. We pretended we didn't have them and that they didn't exist. And then with that bottom 99%, we made some of it. We took some of it for training our model, and we took a bunch of, some of the rest of it for what we call validating our model. And the goal was, well, with the data meant for validation, we can add back in these extraordinary things. And once we've trained our machine learning model, we can see how well we find the extraordinary compounds amongst all the noise. Well, bulk modulus is a continuous value. So naturally, we thought, let's predict bulk modulus and try to find the ones that have the highest values. So we did that, and that's this figure here on the left. I haven't drawn the 45-degree line, but it's that same plot, the parity plot. And what we saw is, well, when it came time, this is the test set, or what we used to validate the model. When it came time to determine if we found extraordinary things or not, we had to draw some lines. So that horizontal line, that was the cutoff that we thought from the training data might represent where extraordinary things could be found. And this vertical line tells us anything to the right of it, those are extraordinary. That green box is a true positive. The blue box is a false positive. And so true positive means our model thinks it's extraordinary, and that's true. The blue box, the false positive, means our model thinks it's extraordinary, but that's false. And then this purple box in the bottom right is our false negative. The model does not think it's extraordinary, but it is. So it was false. And in this case, when we started breaking this and trying to get a good metric for how we were doing, we realized that this isn't a regression problem, it's a classification problem, and people have been going about this wrong. So here on the right, we rephrased the problem. And we, instead of having numerical values we were trying to find, we simply had a label, extraordinary or ordinary. And we did this in the training data, taking the top 99% of that data, or sorry, the top 1% and calling it extraordinary. But then when it came time to the test data, we asked, can you find these additional guys amongst the noise? And indeed, you do better. You have more true positives, fewer false negatives, and fewer false positives, with the rest of the data being ordinary things marked as ordinary. That's pretty trivial. But when you get here, you have a few things to ask. Well, this is a very kind of an easy problem because this data is computational data. And our model had access to a bunch of chemistries. There was no real gap between the best data and the extraordinary stuff. And we essentially treated it like this was a realistic problem. But we got some comments from people that said, well, this is cool. I'm much more interested in whether or not you can do this when you remove elements from the training data and see if you can find them amongst extraordinary compounds. What happens if you remove structures and see if you can find materials with this structure type in the extraordinary data when you never saw that structure in the training data? And then what if there's a massive gap between what you trained on and what extraordinary data looks like? And so we addressed it, and we were, I think, pleasantly surprised to see, again, with shocking accuracy, the model was able to say, it doesn't really matter. And fortunately, what we did here is we used Anton's features. So we had some chemical notion of what CCM was, even if it wasn't in the training data set. And we used as a proxy for structure the space group and the number of atoms in a unit cell, which was a suggestion, and it works in a pinch. And we added this massive artificial gap. And our conclusion was, at least in this data set, this proof of concept, it appears like machine learning is going to do a pretty good job of helping us find those extraordinary materials. And if you rephrase it as a classification task instead of a regression, it's going to do an even better job. And for Dr. Gracer, this is great because if he's going to be synthesizing things, he now goes from having a chance, 1 in 100 or 1 in 1,000 to 1 in 3 or 1 in 4, which is massively better for him when it comes to finding something that he can publish and say, look, this is a material that people haven't studied that's very good at its job. Well, all of this sort of taken together gets a good view on how we've been interacting with the material science community and how we've been sort of determining the, where machine learning falls in with all of it and what things it's really capable of. Well, the other thing we wanted to ask is we've been using these tools, these machine learning algorithms, sort of out of the box. We took them from computer science and we applied them to material science. We asked, can we do a better job if we sort of conceptualize how we do our learning process, but from the lens of material scientists? And that led us to this work, which is the currently submitted work. The other ones were published. It's currently a submitted work, but we're optimistic that it'll go somewhere. And that is what we call CrabNet. It's a great name. I'm very proud of that name. And I just need a shout out to Anthony and Ryan, who helped work with me a ton on this, especially Anthony. But CrabNet stands for the compositionally restricted attention-based network. And compositionally restricted means we only use the chemical composition, which is a good situation because you don't always have the structure, or you might not always have like synthesis steps. And so this gives us a single model that can, do a good job across the board, very general. And then attention-based because it uses the attention mechanism that is very common now in deep learning. And this is really cool. And when it comes to CrabNet, it's actually a transformer in disguise. And I say transformer in disguise because literally CrabNet's attention mechanism is built on what's called the transformer architecture. So steering away from material science, I'm just going to talk about how the attention mechanism works within the transformer architecture and why that's so important to us. So right now the transformer is huge. It's currently being employed by all the biggest names in tech, people like Google, Facebook, Amazon, Microsoft. And primarily it's being used for things like text translation or generation. They call this natural language processing. So I'm going to use this area to sort of give you an intuition as to what the transformer does. Let's take a sentence. This is going to be our system. And then let's say each item in that sentence, or each word in that sentence is like an item in a system. The transformer's job is to build attention maps that essentially allow us to update the representation of an item in the system based off of the fact that other things are in there with it. So you could think of like text translation. If I go from like English to French, sometimes the words might be switched. And so you can't translate word for word. Instead, you have to say, okay, given this English sentence, how should I update my French representation given the fact that there's all these words here and that the ordering might be different? And so I can choose progressively what each word should be in my French sentence to finish my translation. Or text generation. This is, you might have heard of the AI that's too dangerous to be let out into the public. This was GPT 2 and 3 from OpenAI. Well, what this AI does is it takes words and it tries to make reasonable completions of your sentence. And so what it does is it says, I need to update the value of the next word, given the fact that all these other words are in the system with me. And then like the other place you might have seen the transformer is question answering, and this is a Google search. You might have noticed that if you kind of like swap around the ordering of the words when you type into the search bar, Google kind of magically knows what you meant to say. And part of this is because the value of the word in that search is dependent not on its location necessarily, but the fact that other words are in there with it. An example that really drives this home for me is like if I had a sentence with the word to in it, let's say it's spelled TWO, I have no clue if that's the correct word there because people spell two, and two incorrect all the time. So how I update it to the correct representation is I look at all the other words around it so that I know, well, that was misspelled or that was the word I intended it to be. Well, it's cool that transformers work here in natural language processing. But I'm also, you've probably been staring at this little graphic down here. I'm also excited about the transformer because it works in a lot of other places, and we showed it works in material science. So what you're looking at is the game of StarCraft. And specifically, who's controlling these units is DeepMind's AlphaStar AI. And this is a computer that beat professional StarCraft 2 players, which was a task that people in like the community or the computer science community essentially thought wasn't going to happen, probably ever. because this game is very complex, it's partial information. You have strategies that play out over like half an hour, and you have decisions over milliseconds that can win or lose the game and ruin strategies immediately. A nightmare for a computer to learn. But they were able to do this, and a massive reason they were able to do this is because the transformer came on board, and it allowed them to build an architecture that could look at the units on the map. And for each unit, it can update what that unit should be doing based off of the fact that there's other units in the system with it. And so here what we have is items in a system are dynamically updated to have their true value when in the presence of other things. And this is awesome because you can start to see where this is going for material science if you think of chemical compositions. Well, the other example that I just want to point out because it's super fun is image GPT from OpenAI. And again, it updates the value of a pixel based off of the other pixels in the system. And you can complete images to get a cat reading a flyer, or my favorite, I think it's a cat reading a menu at a Japanese restaurant wearing his kimono. But regardless, this whole application of the transformer is incredible because it gives us a lot of super useful things to do. First, because all the big players are using it, it's incredibly well optimized, which is a huge thing. Don't underestimate this. It lets us train bigger models faster with more data. We can prototype, we can focus on getting more and more data instead of having to update our architecture. We can do all kinds of things just because everyone else has made this really easy to work with. Another thing is, since we update items in the system, we never destroy the identity of an element. Where when you make a single vector that represents a chemical composition, the atoms or the elements in that composition, they lose their individual signal. But since we're only updating their signal based off of the fact that other atoms are in that system with it, we can now do some really cool things. We can show direct element-element interactions, and we can show the final contribution that that thing gives us in the materials property prediction. And the last part that was just a nice bonus for us and really made things possible is in the transformer, what things pay attention to, the ordering doesn't really matter. We call that permutation invariance, and that just goes really nicely with like a chemical composition. Al2O3 is the same thing as O3Al2 when it comes to interacting with it physically. Well, to use the transformer, we first had to represent the data correctly. We had to work on getting that big X value correct. And to do this, we created what we called the EDM, the element derived matrix. And that's composed of two parts. The top part is the chemistry or the chemical information. And the bottom part is the fractional information or the fractional prevalence, the stoichiometry of the compound. So when it comes to the chemistry, all we do is we look at the atomic number. So for aluminum, it's 13, for oxygen, it's 8, and we go to a database. This is, in our case, the Matt-Tvec embeddings. These represent some notion of like physical similarity. And we grab the associated vector for aluminum and the vector for oxygen, their representations as elements. And we put them in the correct row. We go to the prevalence part, the fractional prevalence. So aluminum, it's 40% of the system. Oxygen, it's 60%. So we put it through a fractional encoder to expand it to the dimensions which we dictate at, and we call it D model. So once 0.4 has gone through this fractional encoder, essentially it's a bunch of sine functions that it goes through, and we get a high dimensional representation of that value, 0.4. Same with 0.6. And we now have these two matrices, the one in green and the one in blue here. If you add them up together, we now have a row for aluminum that has its chemistry and its fractional prevalence. Then the second row for oxygen has its chemistry signal and its fractional prevalence signal. And that gives us an EDM, and we just have to do it for every single composition, chemical composition in our database. And once we get to here, we can think of each matrix as a system and each row as items in that system. And we're going to be updating the items based off of the other things around them. And let's look at how you do that with a transformer. The first thing is you take an elements row and you project it into what we'll call a high dimensional space. Not super important, except for it's going to give us these cool things to work with. The first projection will give us what's called the query. And the second projection, a different projection. And these are learned by the neural network itself, so we don't have to do any math here. We just have to set it up. The second projection is going to learn a key, and the last projection is going to learn a value. So the query is a vector, think of an arrow, that is going to be used to ask everything else in the system, how important are you to me? Should I pay attention to you? The key is going to be the answer to that question. It's another vector, and if they overlap with each other, the answer is, I'm important, pay attention to me. And then the value is what's going to be used to help us get the materials property at the very end. This is my value coming in. This is how I should update based off of the fact that you're in the system with me. So let's look at this. We have aluminum sending out its query and aluminum answering with its key. So how important am I given the fact that I'm in a system? Well, that's the AL-AL interaction. We have aluminum sending out its query, and we have oxygen sending out its key. And that's now AL-O interaction. So that's aluminum looking at oxygen. Similarly, we can have down here in the bottom left oxygen looking at aluminum, the O-AL interaction. And then we can have oxygen looking at itself, the O-O interaction. And so now this square matrix here, that's going to be the basis for what we call the attention matrix, which tells us how much attention things are paying to each other. Now, before we can do that, we're going to say that you can only attend a total of 1, which means we're going to say for each element, we're going to normalize that row so that the sum of all of the columns for that row equals 1. And we do that using a softmax function. It's not super important if you don't know what that is. But once we know what to pay attention to, we can multiply this by the values of each element and essentially update our element values so that we now have aluminum and its new representation in the presence of oxygen. And we have oxygen with its new representation in the presence of aluminum. And of course, they're in the presence of themselves as well. Well, all of this slide here, it can be summarized as this gray box. Now, you see Z appears more than once, which essentially means we just make more than one query, more than one key, and more than one value. And we do that for as many what we call attention heads as we want. That is, we make as many attention matrices as we desire. And this is important, and this is useful because as we have more of these, we get different perspectives on the problem. Essentially, we can attend to different things in the system, and we can, at the end of it, after we have all these different attention heads, we can kind of summarize our attention, get things back into the dimension they came as, so it looks like we just started, and we can repeat. And that's this times n over here. In CrabNet, we found that 4 attention heads repeated 3 times does a really good job of learning across a ton of materials properties without making the machine learning model like too big or too bulky. Well, once you arbitrarily decide you're done, we call that final output this EDM double prime. It looks like the input, but now each row for the elements has been updated to represent that element in a specific system. And we take that and we put it through a simple, fully connected residual network, and we take the dimensionality down to 3 values for each row. So the first column represents our prediction of the materials property. The second column represents our prediction of the uncertainty with the associated with the first prediction. And then this third column contains logit values. We're going to ignore those, but they're useful in problems that have classification aspects to them. Well, once we have a prediction associated with each element, we call that the per element contribution. Here on the right, we simply take the average of all per element contributions to get the materials property for the entire compound. And then to get the uncertainty associated with our prediction for that entire compound, we can do the same thing by averaging the per element uncertainties. And so this framework, this whole system, essentially is what CrabNet is. And we wanted to see how good it was. So we consulted a bunch of databases and we collected a very large set of data to test on. These are some of the data we looked at. 3 of these are computational data sets, and the map bench is a mix of both. But really, this table summarizes what those data look like. We have some data as small as 300 here on the right-hand middle, this steel citrine experimental. So an incredibly tiny data set for like deep learning. And then we have data in the 300,000s. And that seems a lot more reasonable for what you might expect when you hear a neural network. Well, given this data, we decided let's compare it to some of the best practice approaches. And we decided those were Roost, the far left column here, which is a graph neural network approach. And then the other one is ElemNet, which is a neural network that uses fractional information. So I have Roost and CrabNet here, and those are the two to compare against each other because they're sort of similar in their formulation, and they both start with this notion of chemical information using that mat-to-vec embedding. On the other hand, we decided if we're going to compare to ElemNet, who has no chemical information, let's go ahead and build a CrabNet that only uses a one-hot encoding, hence the name hot crab. Well, CrabNet does about as good as Roost, and hot crab sort of destroys ElemNet. And then to really keep things grounded, to make sure our results look like everybody else's, we built a random forest regression trained on the magpie features. And this is what people call classical learning with domain information. Well, this kind of summarizes things. Any value below 0 is a win for CrabNet. So on this upper left-hand side, we see that Roost, it's about the same, but CrabNet sort of edges it out. In this bottom one, we see very clearly how hot crab, despite having no chemical information whatsoever, sort of destroys ElemNet. And I think there's one that's worth pointing out that's actually a little hard to see in that figure. This very bottom row, Steele's yield, this is the 300 data set, or the data set with 300 items in it. And more than just that, Steele's yield is a nightmare to learn on, or you'd expect it to be, because it has up to, I think, 12 elements in a chemical composition. And it has fractional prevalence amounts as low as the thousandths of percents. Now, despite that, well, that's actually a really difficult problem for Roost to solve, and you see it doesn't solve it. But because of the way we formatted CrabNet, and because of the way chemical information propagates to the network, we can see that both CrabNet and hot crab actually beat the classical method as well, which was super encouraging because this is, typically people would say you only use deep learning when you have lots of data. But even if we're doing as good as Roost, CrabNet's it's special. And it's special because it gives us that direct attention to, or that direct access to the attention mechanism. And we get those learned contributions and uncertainties. And so let's just finish things up by looking at some examples of this. What you see here is a CrabNet model that's been trained on bulk modulus. That means it learned how to do the attention. It learned what elements were important to each other. And if we look into the first layer and look at those 4 attention heads I talked about, the different perspectives on what's important, we get these plots, these heat maps. And I'm just going to go through them really quickly for you. First, attention head A, we see how much oxygen looks at oxygen compared to aluminum. And so I'm going to kind of anthropomorphize here. I'm going to tell a story, and it might not be a true story, but what's, I think, just impressive in and of itself is CrabNet lets us tell any type of story whatsoever. So here I'm thinking, okay, so bulk modulus, kind of like the incompressibility, oxides are typically incompressible. So if there's, or like have high incompressibility. So if there's oxygen, it's probably an important thing to know. So oxygen is going to say, okay, I need to pay attention to myself because I'm here, but I'll pay about 30% attention to aluminum. Aluminum is going to say, oh, there's oxygen here. That changes things because I'm a metal. I'm typically kind of soft. And so aluminum's mostly going to pay attention to oxygen and very little to itself in this first attention head. That's the first perspective of the problem we see. The second attention head, oxygen is going to say, okay, I need to look for aluminum. That's actually important to me. I need to have some signal. I need to update myself based on the fact he's here. I'll pay attention to him. Again, aluminum's like, oh crap, oxygen's here. I need to have oxygen information to be correct. The third attention head C, oxygen is like, I'll look at both of you. You're both important to me. And again, aluminum's like got these alarm bells going off. And then finally in this last attention head, aluminum's like, okay, I know oxygen's here. That's like the other attention heads are paying attention to that. I need to at least have some of my own signal so that I don't lose my aluminum-iness. And even if this story is completely made up, even if this isn't the actual interpretation we should walk out with, CrabNet gives us the ability to have this story to start. So What else can we do with this? Well, we can look at it on a global scale instead of on a per prediction scale. So this is a result of looking at what silicon pays attention to, so the row for silicon, in a model that's trained on band gap. So silicon and band gap have kind of gone, hand in hand together since the beginning of all of electronics. And that's because when it comes to silicon, you can add what we call dopants to change band gap, to change the band gap. And indeed, attention head A, our model says silicon, what's important to you? And it says N-type dopants. So that's great. We have the story already there. We knew that story coming in, but now we see we can physically go in and verify what our model's doing, and we can say, I trust that. That makes a lot of sense. We go to attention head B. We ask the same question, silicon, from this perspective, what's important? And I don't see any real patterns here, but it's kind of saying, well, these metals are kind of important. Like, I don't know, wishy-washy, but maybe that's because I don't have a good enough understanding of this system. And maybe even someone who came in knowing nothing about doping silicon could walk out and say, okay, these are the atoms that are important to look at. We go to attention head C, its perspective says transition metals. Let's look at those guys. When I'm in a system with them, they're obviously important. And then attention head D doesn't look much at anything. So it's possible that we didn't need this attention head, or it's possible that these few that are highlighted are important for determining the band gap of a compound that has silicon in it. Well, I also talked about per element contributions, so let's look at them. This is the average of what an element contributes to the prediction of bulk modulus. And this is good because it matches expectations. When you think of hard materials, you think of tungsten, you think of carbon, boron, nitrogen. And indeed, these things on average predict or contribute quite a bit to our prediction for high bulk modulus values. But we can also look at, instead of the average, the individual predictions. This is a distribution plot here on the right. We see lithium, it never really predicts much of anything. It's always a very low value. It's a soft metal. And we look at tungsten, one of those guys who's awesome for this task. We see it's mostly awesome for this task, but indeed there's these two modes that are not incredible. And this is worth talking about because we can visualize these individual contributions and we can see that tungsten's obviously behaving very different here. And I went and looked it up, and I think it was tungsten sulfide, and it's like a layered 2D material, very different than the other versions of tungsten we're used to seeing. And indeed, it's used as like a dry lubricant. Well, if we look at like oxygen in the same situation, oxygen is kind of all over the board. It's mostly associated with high bulk modulus values. It can be in some compounds that it doesn't really contribute much of anything. But what's cool is, I think because we have so much oxygen in our data set, the uncertainty is relatively low with oxygen. So it's about 5% uncertain with its predictions, which for us as researchers just kind of allows us to know whether or not we should trust that prediction at the end of the day. And kind of the last thing I really looked at, and the last thing I'm going to show you guys, is I asked, well, since we have this awesome tool, and since it generates contributions and uncertainties and these great predictions, what happens if I make a bunch of predictions and look at a system? So what I have is a binary system, meaning there's two elements. And the x-axis says, the far left says, this is what pure oxygen looks like if there's some silicon signal, which doesn't make much sense, but it's how we have to frame this. The left is pure oxygen. The right is pure silicon with some oxygen signal. And then everywhere in between is, different, it's a smooth interpolation, different fractional amounts of oxygen and silicon in a system. And the y-axis is the prediction of the band gap value. So a good system to look at, because silicon dioxide's a useful one to know the band gap of. And when I was investigating this, when I was visualizing this and creating these figures, I noticed something that was very wrong. And I think material scientists here are probably going to see it too. The big red X. Silicon dioxide, we know it has a band gap of about 6 electron volts. That's just reality. Our machine learning model, it's predicting about 2.4. You can't see it because the resolution, it's a little choppier than actually shown. And our data set, so the labeled data itself, says it's a metal, which couldn't be more wrong. And because I was visualizing this data, and because we were looking at these uncertainties and the contributions, which uncertainties in gray, contributions in blue and red, what we actually saw was CrabNet gave us a nice, pleasant way of visualizing it, and I could go through binary systems very quick. Well, it also gave me a way of seeing blatant errors that I otherwise wouldn't have noticed. And in fact, I think 3 other publications have used this data, and none of them have noticed that this error is in there. Well, the people that collected it, I think what happened, and I don't know too much about how these calculations are done, but they grabbed a value of 0 for silicon dioxide and that one next to it, neither of which should be 0. And I went to the database they claimed they grabbed it from, and they said, well, 0 is the value associated with the relaxed calculation, but the static calculation had 6.3 electron volts, what you'd expect from silicon dioxide. And so here, now what we have is something very different than what we expected to be coming out of with CrabNet, but it's a good way of us just looking and verifying our data. And I mentioned this earlier, now I'm going to go through and say, well, how much of this data set is wrong and how much better can we do when it comes to learning if we fix those things? All right, well, I have some contributions I thought were associated with CrabNet and kind of reflect a lot of the research we've done here in the Sparks lab over the 4 years I've been here. And this is a lot of text. I'm not expecting you to read it all at once, but I think it's appropriate to open the time up for questions now. And while people are answering questions, you can go ahead and read this in the background.
So it's our public Q&A portion. After this Q&A session, we're going to excuse the non-committee members, and then the committee will have a chance to ask questions to Ka'ai. So if you're not a committee member and you want to ask a question, now's your chance.
Do we get to ask him hard questions?
Absolutely, let it rip.
I don't know if I have any hard questions. So I do a lot of machine learning in my work as well. And the biggest critique or problem is, like, how do you walk from the machine learning world and the conclusions that you can draw from data analysis to things that you can implement in the real world? So can you just comment a little bit about, like, how you're using these models, what conclusions you're drawing, and kind of how you envision passing them to real world validation processes or applications?
Yeah, absolutely. So I mentioned the work where we talked about finding extraordinary materials. Now, this is one of my first attempts to see if we could even do it. It's like, I would say maybe irresponsibly, people in the machine learning world have kind of said, hey, look, if we apply these algorithms to materials data, we get results, we get R2 values of 0.9. We can expect to find materials with 60% accuracy. And there's dozens of papers that say this, and only 3 or 4 papers that are really strongly say, look, we did this and we found them. And Anton's a really big, one of my committee members, I think he's here. He's a really big proponent of, you do machine learning to do synthesis, and then you publish. And we kind of tried to do that in the Sparks lab as well. We've had a lot of issues with machines and some failed attempts, which is what you'd expect. But that first paper was just trying to quantify if it was even possible, which I think was a good first step. And then the other thing that's really an issue is you have this problem of either your predictions are so obvious, why would you use machine learning? Or your prediction is so unintuitive, how could you trust it? And I think that's where CrabNet kind of came in, and it's kind of why we wanted to design something. We built it with this inspectability in mind, so that at least when it comes to generating a prediction, you know where the values come from. You know what elements are supposedly helping, what are hurting, and you know what elements depend on each other in a system. And that gives us some steps forward. Now, in terms of getting this from the machine learning theoretical spot to a workstation to synthesize, there are a couple problems besides just, does the machine learning work and have people overpromised it? And one of those is, it's hard to know if the chemistry will actually come together. You can propose any combination of elements you want, but physically that doesn't mean they exist. And so that can just be wrong. And so you need a way of validating whether or not something's stable, which people are working on, and we hope CrabNet's a step towards that. You can predict formation energies. And the other problem is, well, if you just have a database of things that are stable, and you're screening through those, you're not really discovering much that's new. You're just you're repurposing an old material, which has its merits. And I think Dr. Sparks showed, I think, 3 materials that were classified as super hard materials using this process. But at the same time, those typically ended up being things that were obvious in hindsight. They had the elements that are just, the elements you always see in hard materials, just combined a tiny bit different. I'm not sure if that answers it exactly, but those are my thoughts regarding the problem. And it's kind of what we've done so far to address it.
Thanks.
I had a quick question on
Yeah.
your paper where you found the extraordinary properties, and you had those 2 lines that divided between, the true positives, the true negatives. How did you determine where to put those lines on the graph?
That's a great question. I kind of glossed over this. There is some subtlety to it because you can't use the test data to do that. So what we did is when we made our training data and separated the test data, like those ordinary and extraordinary things, we made an additional separation from that small group of ordinaries. And we essentially ran that problem again. We had an additional data set that had the top 98%, or rather 98 to 99. And we trained on the bottom data. We used what we'd call the validation data to draw those lines. And then we brought the test data in to see how well those lines did on the test data that were drawn on the validation data.
Can I ask a quick question, Kai?
Of course.
So I hate to throw you like a softball question or anything, but I really am curious. If you had a second go at making CrabNet or attempting to even market it commercially, what would you do differently in hindsight?
Oh boy. In hindsight, the biggest issue with CrabNet isn't its current architecture. It's not its current ability to learn. It's the amount of time we spent trying to build the tools ourselves. So when we first started CrabNet, we built the entire transformer architecture from scratch, which was necessary because it wasn't until 3 months later that a good public version was made open source. Well, I would say my biggest regret is being first ignorant to that for about a month and then stubborn that I could do it myself better than Google. And so I spent like 3 months working on my own implementation that was just a little slower and worked just a little worse because of some small little tweaks that aren't addressed in like the main paper.
So I guess as a follow-up question to part 2, where would you want to take CrabNet? Not just small optimizations, but either new features or ways that you could see it being majorly improved upon.
Oh boy. I can't say there's much more I can think of, or I would have already tried it. There's been 1,000 deaths of little ideas involved there. Things as simple as how do you represent the fractional amounts of the elements to things as like big as what's the ultimate ordering of how you like perform operations, like when do fully connected networks come in, how many layers, like a lot of small tweaks that people have made in like natural language processing that we tried. I think, I don't think there's anything right now that I could really talk towards going forward because we tried so many things that didn't work in the past.
That's for me. Thank you.
Any other questions from the public before we go to the private committee questions? All right, well, thank you everyone so much for joining us. So I'm gonna go ahead and ask anyone who's not a committee member to say your congratulations and then head on out. And we're going to then ask Kai some questions just as committee.
Thanks, everybody.
Good job, Kai. Good luck. Talk to you later.
See ya.
Thanks, Kai. Congratulations.
Okay. So Dimitri was here for most of the talk. He had to step out about 10 minutes ago. He said that he had somehow missed this on his schedule, and he apologized profusely, but he said that he is completely fine with this. He's going to watch the recording, and if he's got any final questions, he will send them to you, but he's fine to give his opinion once we have a chance to deliberate. But we do have Bay and Anton, so we have we've had 4/5 during the presentation and 3/5 of the committee during the private session. So I think we have a quorum. I'm going to call it a quorum. And I'll turn the time over to Bay and Anton if you have questions that you'd like to ask Kai.
Yeah, so I made a list of a few questions. Maybe let's start with CrabNet. So the first question is that, given that there's so many open source implementation, there's also state of art. Is it possible to take one of those existing open source transformers and then use your EDM, right? Like, it feels like there's a lot of energy initially to try to kind of, if I'm thinking about the whole effort of NLP, where they do like word2vec and all this, glove and bird, and part of the energy is how to take your raw data and map into some sort of input that neural network can work with. And I feel like that's my understanding of your EDM, is how do you translate your material science data into something that transformer can work with. So my question is, if you take your existing EDM, is it possible to take it and take some transformer implementation out of the box and train it to kind of have a sort of, in some sense, open source CrabNet, not necessarily your implementation of the transformer, but another version? If that is not the case, what specific implementational detail you need to focus on? Is there any extra tweak inside CrabNet that have to take sort of the nature of the data into consideration, right? So
Yeah.
It's actually two questions. Is it possible to take EDM, fit into out of box open source transformer, and still kind of, I'm talking about how general this framework can be done, or how dependent it is on your current implementation?
Yeah, so when we first started working on CrabNet, I think it was about a year ago, and maybe I think it was a little longer even, and that is indeed when we built everything from scratch, and it worked pretty well. There was a few moments during CrabNet where we had some major bugs, as there always are when you build something like this from scratch. But once we had a final version, it was doing fairly well. And it was, I don't know, maybe a month or two after I'd learned that Hugging Face, I believe it was, had implemented the transformer architecture. And then PyTorch had added it to the official repository. And so at that time, we looked at using their work. And the first major thing we found was, when we had built our architecture, we built a version of the EDM, what I originally proposed to you guys during the dissertation proposal. And it worked very well with ours, but it did not work with theirs. And that was, a little discouraging, but we were also fairly certain that if we could get the PyTorch version to work, it would be better. And so the current CrabNet version, it does use the PyTorch transformer encoder layer. And it repeats that layer with different initializations 3 times, initialized with 4 heads. And so we have now used that layer, and it required us to tweak the representation of the data just a little bit. Previously, we've been concatenating the chemical, or the prevalence, the fractional prevalence information. And that had worked in ours. We don't know why. We think probably just micro-tuning on the validation set, changing things like where dropout was inserted that might have been a little different from the original publication, or things like when layer norm was performed. But when we went back to the PyTorch version, we decided, well, let's see if we can start from scratch and do things as similar to the paper "Attention is All You Need" by Vatswani et al., the original work. And it was at that point where we took the positional encoder, we repurposed it for the chemical, or the fractional prevalence. And instead of going to up to so many places a word could be, its position 0 through 100, we instead said, well, fractional amounts can go 0 through 100. So we can discretize this with certain resolution. Now that destroyed some of the things we thought CrabNet would be good at, which was like identifying dopants, because we had like a specific column or columns with the fractional information. But in their paper, they showed that if you take the addition of the signal plus the encoding, that fractional encoding propagates through the network much better, like through the gradients and stuff. And we found that fixed our problem in terms of learning with most data sets. But like that Steele's yield data set, it had some issues still. And so to solve that part, using the PyTorch transformer encoder, we had to think of the positional encoder in a different way. And we ended up doing like a positional encoding for the absolute fractional prevalence and a positional encoding for the square of the log fractional prevalence. So then we can have very small data representations, dopant amounts in one half of the signal that's added to our chemistry. And then the other half, we can have like chemical compositions in like a linear scale added to the chemistry on the other half. And so to answer, essentially, we had made changes, and they were small changes that worked with our original EDM. We decided for performance issues and for the sake of people being able to quickly reproduce things and to understand what ours was doing, it was much better to try and move over to the PyTorch version. And when we did that, we decided, because it wasn't working as well as it was with our initial build, like our initial architecture, we decided to reformat it to work in a way as similar as possible to the NLP problem statement. And when we did that, we saw an even higher improvement to learning, and that like pushed us just a little bit better than Roost at that point. Where before we had a few properties where we matched. I'm not going to call Roost state of the art because they do a great job. We'd matched Roost and we were proud of that. We were happy enough since we had all those additional visualization tools. But once we used their stuff and tried to just, make it more similar to NLP, we got even better results.
Yeah, I guess this is a really great answer, but I think this is more out of curiosity in the sense that as a transformer architecture, for example, the one that is done by the Hugging Face, right? That one so far is still sort of seems to be the front runner in that space, and it does provide where for NLP purposes for both PyTorch and TensorFlow, right? So the thing that as more and more newer architecture come into place, I was wondering if CrabNet can be designed in such a way that there's sort of a modular components where when there's a newer sort of architecture, you can kind of take out your old architecture, kind of plug it in, right? Of course, I'm saying it's in a very sort of simplistic version, but the hope is that, as more and more architecture became more and even better, that you still keep your CrabNet, but you have the ability to switch in and out like a modular component to kind of take advantage of the latest advances in that space, which on the same way as what you just described, you have already done, kind of have CrabNet kind of evolve as a transformer architecture evolve, where to kind of take advantage of what's happening, right?
Yeah, no, of course. I hadn't even thought about that fact. And it's definitely true that better versions are at least being worked on. I'm not sure if there's better ones than the Hugging Face right now. The only thing that would stop us, it's drop and play. The only thing that would stop us is if it wasn't compatible for a few of the keywords, like if APIs changed, because we do have to do some clever masking on the attention maps and on like the key value representations that go in. And that's just because rather we wanted to batch with any arbitrary number of chemistries. And there's a problem with, really, I'll call it a problem. It's not really a problem, but there's a problem that you have different sized sentences, or rather different numbers of elements per composition. And to batch, you need a fixed number of rows. And so that's really the source of like a lot of additional like keyword usage inside of those architectures. And it's kind of interesting and worth talking about. The other thing that I think CrabNet could be useful for, and I don't know the full capabilities of what the current transformer architecture is like, is predicting on crystal systems. And a brute force way of doing that would be to simply represent the sites, hundreds of times. And that's not totally unreasonable, but I know that like your attention mechanism computationally it scales at the square of the number of rows, since you make that attention matrix row by row. And there are techniques that are fixing that. And I do wonder if, I mean, first off, I'm currently working on trying to do it with the crystal system. But I do wonder if those newer versions, when they come out, can be more useful to us, just because we're not running on industry hardware. We're running on, you know, a couple GPUs on a workstation.
Yeah, I'm psyched about that. I'm really excited to incorporate graph representations of structure and send those through the net. That'll be our next work.
Yeah, I'm trying to understand your notes. Graphs.
Yeah. No, I'm just
so very
pumped about
excited.
it.
Yes. All right, I'll give Anton some time too. I have the other smaller questions, but this was my main question.
Kai, it was like fantastic presentation. I really like it. And I'm very flattered that you decided to name the features after me. So you're doing way better job marketing me than I would supposed to do. But anyway, so I really like how you explain it, transformers and how they're used everywhere nowadays. And I'm very familiar with Alpha Star, the one that plays StarCraft. So probably you didn't know that, but back in the day, probably like 12, 13 years ago, I made money playing StarCraft. So it really resonates with me. So I also played again.
Anton, I've known you at least like 7 years. How am I learning this now?
See, I was young and I needed some money. So don't judge me on that.
No, zero judgment.
I watch StarCraft every day.
So, but I don't spend so much time playing StarCraft 2, but I tried it against Alpha Star. So I read their paper in Nature. It's very nice approach and it's very nice description of transformers, what they do. But the main critique from players is that Alpha Star is so good because it does a lot of actions per minute. And basically it discriminates against humans for being humans. So it just can do it faster. So it's not necessarily that the strategy is better, it's just because it can do it faster. So my question,
though, right? Didn't they actually put a cap on it that was less than a human, like a pro?
Yes, but the effective actions per minute still will be better, even if you even if you keep it. So that was the main critique, at least from people that I spoke to. So my question is, so suppose, just imagine the situation that I'm not like AI believer, and I also say, well, for example, like your materials discovery, CrabNet, it just does not better, but faster. Just imagine that situation, right? What would be your response, and maybe some specific examples that, okay, we found like a new way, new strategy, like thinking out of the box that we can just show to you as non-AI believer that it actually works, it works better, not just faster?
Yeah, so kind of I'd approach it in two ways. First off, I think working faster in and of itself is, if it's, let's call it its strategy. If its strategy is even remotely close to the level of performance as a human, if it gets 50% of the ones that a human might also suggest, then I think that's a great advantage. And there's no reason, since these aren't competing, you're not competing against the computer. You're competing with the computer against essentially like, the progression of humans through time. So the fact that it's faster only gives us the ability to go through less data using our better strategies. Now, I don't think I'd make the claim that it's better than people. I think if you sat a scientist down and if you sat CrabNet down and you said, go through these million pieces of data and find me the one that's the very best, it would be probably competitive. But I think someone like yourself, not me, I don't have enough experience doing synthesis, but someone like you or Taylor would probably say, well, I know that these ones are good candidates because they're physically realizable, and they're good candidates because they match my intuition. And I say intuition, I think what you guys are typically doing and what I do is I'm looking for elements that I know are associated with this problem or are similar to ones that have been in the past. Now, CrabNet's going to pick those same things up, but it's going to do it sort of indiscriminately. And ideally, we can add some additional stops on it. One thing is we can predict formation energies, and we can predict them, or let's say the enthalpy of formation, and we can predict that decently. There's a paper that shows that if you have structure, so if you use like CGCNN, you can predict it fairly reliably, but without it, it's kind of, I'll say 50-50, it's probably worse than that. But if we can incorporate formation enthalpy predictions plus a prediction on how capable something might be, then I start to wonder if a human might be at the same level as CrabNet, but might take 18 months, whereas CrabNet takes 0.18 seconds. So I don't think it's better. I don't think it's going to replace anyone. I think it's always going to be supervised by people. I think the extent of supervision will slowly be let off as it's continually showing to have good results.
Thank you. That's very nice answer. So I have another question. As you mentioned in your presentation, the main source of data, basically in material science, is first computation, second characterization, and third it's imaging. So imagine that you're constructing like a model, and you can actually see what actually data it uses and how it makes its decision. Just imagine the situation, and suppose you see that there is like a conflicting answer based on one type of data and the answer based on another type of data. So for you as an experiment, not maybe experimentalist, but as a material scientist, what data would you prefer to work with, or like which data would you trust more? Is it computational based on our previous knowledge? Is it characterization, something that we can probe indirectly, or is it imaging, something that you can see with your eyes?
So I'm gonna kind of treat this as if it's like a trick question a little bit. And the reason I'm going to do that is because we have way more computational data than we do characterization data. When it comes to image data, we have like a lot of steals, like microstructure stuff, and that's about it. And typically it's like, I don't know, with yield strength. So there's two ways of looking at this. One, if I had infinite data for all three domains, I would, and when we say characterization, I'm going to say we have the synthesis route and the chemical composition, and maybe even let's like when we say characterization, do we get to have the crystal structure? Like, can we refine that? You know what I mean? So like, let's just say it's chemical composition and whatever physically measured value we have. Infinite data, I'm always going to go with what you measured on the machine. My intuition is that unless we also have infinite compute with DFT, our estimation of reality is better if it's characterization. And you can look at the manufacturers and grab the book for each machine and see what their errors are, and you can see what people have published DFT errors to be, and you can go through all of that for any property you'd like. But that would be my starting point. Now, when it comes to images, we have this thing where I do like the idea that we could apply like a convolutional network to your microstructure. And if you have, I assume you've done characterization to get the target property with that. If you have that, then you're probably better off learning from an image than you are from the chemical composition plus synthesis route. And so I would say I would trust what our convolutional neural network said more than I'd trust what CrabNet said. And I would trust what CrabNet said more than I'd trust what like CGCNN said, because if it's computation, it has a CIF file associated with it, or like a XYZ file if it's molecular. So I would trust the CNN over CrabNet, which I trust over CGCNN. And that's just because of how accurate, first, the representation is in terms of the image, and then compared to calculation versus, measuring it in a lab. Yeah, that's my answer.
Yeah, thank you for the answer. Just wondering, like, what experimental technique do you trust the most? So what gives you pleasure working with, like, with that data from that technique? What do you like?
So in terms of the things we've measured, the ones that are least reliable has been Seebeck effect. That thing seems to rely on too much stuff going right. So you get like compounding errors. Thermal diffusivity has been pretty reliable for us. Heat capacity with the TGA is pretty good. And yeah, I mean, electrical conductivity, if it's conductive, is super easy. But yeah, I mean, it really just depends on how much you paid for the machine and how many properties have to come together to get it right. If there's doping involved, you're going to get all kinds of crazy results because it's hard to consistently dope the right amount. Like, or if, yeah, I mean, if doping affects the property itself, then that's a hard one.
Thank you very much.
Kai, I've asked you questions for 4 years, so I'm gonna defer any questions I have at this point. All right, any others from Bay and Anton?
Is Olia going to ask some question?
It's me. It's my second computer. So
You have two identities. Okay. All right. So I have a question with earlier slides. The ensemble DFT models.
Yeah.
Could you tell me a little bit more? Because this is a nice picture. So you're saying that, okay, instead of just learning sort of simulation data versus experimental data, I'm going to try to take strengths of both. And then somewhere in there, you talk about ensemble DFT models and how that showing to be doing better. So can you explain to me a bit more how you build that ensemble? Right, because I feel like that detail really matters of how much weights do you put in each of those model in your ensemble, and how you actually train that. So if you could give me like a little bit more detail, that would be great.
For sure. So for this, what we were essentially trying to do is, well, there's two things you could do. You can ensemble, so you can build models on all the different data and try to ensemble those, or you could do, I just blanked on the word, multi-fidelity modeling, where essentially you weigh each of your data different amounts for your model. And the first approach is just much easier, much cleaner, much more understandable for other people to read and to implement themselves. So we thought we'd go with that. Now, when it comes to actually ensembling the models, in fact, let me go back one slide. We had three schemes plus a baseline that we tried. The first was just like basic model ensembling, Kaggle stuff. Let's do a few different learning algorithms, apply it to the data, get these models. And we went with a meta learner on top that essentially just applied a different weight to each of these, and that's dynamically learned. So scheme one is all experimental data. This next scheme over was, we train these models. They marginally improve our estimate of experiment like you'd expect from a Kaggle competition. Let's try to bring in the DFT data that we know exists, that should be useful, that hasn't been used by anyone yet because it's slightly incompatible. And let's add that in. So it's literally, and I think we actually used a neural network because there was so much DFT data. But literally, we took the 3 experimental models, we trained a neural network, validated on that, made sure that there was no experimental data in the training process or validation. And we dragged that model out, took our test data, generated predictions from each model and fed those into this meta learner. Again, it's an SVR on top of it. It learned the weights and it learned how to combine the DFT with the additional experimental models. And then the third scheme, scheme 2, you could expect does the best, and it does. And then that third scheme was to say, well, I mean, it's a little silly to squeeze out 3% improvement. Let's just get rid of the extra decision tree methods. And let's just see how the SVR plus the DFT models do with this meta learner on top of them.
But to be fair, your notations, SVR in scheme number 3 is the one that is trained on experimental data, and then DFT is the one trained on computational data, right?
Yes.
Am I getting it correct? So instead of using 3 different kind of models on the experimental data, you just say, let's just use one of them and one of the simple ones.
Mm-hmm. That's correct.
Okay, so then you're saying that, I see, okay. So
I would say kind of the key here is I'm not trying So like how you could think of this problem is I'm trying to learn the difference between DFT and experiment. And the problem is, that difference is something a model can learn. And you can do a good job. But the problem is we don't have DFT for any arbitrary chemical composition. We have to sit down and we have to run that simulation. And depending on the type of simulation you run, it can take a week, or it can take, I think I talked to a guy who was doing it for 9 months with very few simplifying assumptions. But let's even put it in that week range. Maybe it's even 2 days. That's still sort of unreasonable to expect someone to run DFT for every calculation or every machine learning prediction of experiment that they want. And so the idea is we're learning the difference between DFT and experiment, where DFT is a model trained on it that we show does as well. And I'm going to put an asterisk there because we might lose some correlation to reality since it's like on both sides of the line, and we're not sure if the model is going to be like when our prediction of DFT is like off in the positive direction, we're not sure if that's going to match like DFT's error relative to experiment in the same positive direction. So we might cancel out some nice correlations between the simulated data and reality. But if we model the simulated data, we at least can get you it in milliseconds for any arbitrary composition.
In your experiment, did you see examples where, is it always the case where you added sort of DFT in addition to sort of the model built on experimental data? Is it always the case that you're going to get some form of improvement that is sort of in some sense statistically significant? Or there's examples where it doesn't help? So
I didn't formally measure statistical significance in terms of like a p-test or anything. What I have here is, I believe it was 5-fold cross-validation, and this is the standard deviation associated with those results shown in the grade outline.
Yeah, so my question is basically coming from this plots where we have the ensemble of DFT, and I think you just explained to me how you do this ensemble. So yeah, sorry, go ahead.
Oh, I was just gonna say, and we repeated this a couple times just to make sure, because this is the figure we put to publication, but we wanted to see if this was always the case and if these error bars didn't fly out of the range, and they never did. They were almost always exactly the same, depending on the seed you use, I should say, for k-fold cross-validation. And with the data we have, I noticed this earlier, and I'm not sure why this figure, I'm sure in the paper it says this figure only goes to like 1200. And we probably held out the test set and did 5-fold on these 2000. But yeah, where does that go to? 1100. But I think regardless, with the data we had, we never got to the point where DFT didn't help. I imagine that if we were able to gather another 1,000 data points, we'd almost certainly be in a region where you might as well just train on the experiment.
Since we are on this graph, just a quick question, like, well, why did you decide to plot y-axis in logarithmic scale, I would assume? Well, the root mean square, the y-axis in electron volts. Is it like logarithmic scale?
I had not noticed that before.
Yeah, it looks like it.
Scaled linearly.
So what was the reason for this? Why did you decide to plot it like this?
It's been long enough since I made this figure that I honestly can't tell you.
Yeah.
Wait. I do know why. We were asked by one of the reviewers to make it a learning curve. And so the slope of this represents the expected improvement as you add more data to your model. And when they asked for that, we had to make it log to be, I assume it's a theoretical thing, but to be like appropriately set up to be a learning curve. Okay. And I mean, that kind of answers Bei-Wang's question as well, because if we extrapolate out here, we could probably find the value on the x-axis where these things cross, or at least, yeah, I'd say where the mean crosses, since the training data gets more and more homogeneous, like it's more and more similar, more and more correlated as we go out. So I expect, yeah, I mean, yes, it's a learning curve. That's why it's plotted log.
The x-axis is also log, right?
Yeah,
I think both of them are.
And I think that's the requirement if you want to try to extrapolate out to see where these two things cross, which would be where you don't benefit from from using one over the other, which answers your question really beautifully. And I think Anton said that on purpose.
So yeah, so I actually don't have any question left. I think it's a really well organized, polished defense. So I think great job. I think usually at this point, this is a question is that what your future plan is kind of question, like where are you going to go from here? Now you're going to be called doctor soon. What is the future plan?
I would love to talk about that because I love bragging about my wife. She is in medical school and she graduates in May. So the future plan is to end up wherever she gets matched. She's an incredible student, and I have to brag. She's interviewed at like Duke, University of California, San Diego, Brown, Emory, Vanderbilt, like all kinds of Ivy Leagues, all over the place. But it's also everywhere from Hawaii to Maine. So the future plans is to be quick and agile and make the most of wherever I end up. I think academia sounds kind of good to me. I really do. I found towards the end, I really like research when I'm not taking classes, but maybe when I'm teaching classes, I won't like it as much. And, we'll see. Making money would be nice.
Yeah, I mean, I have a comment on Duke since I went to Duke. I think it's a great place. The difference between here and Duke is you have to get used to the humidity and a little bit more humidity, not as bad as Houston, but more humidity, a little bit more bug. But otherwise, it's a very livable place, meaning that surrounding the campus, there's like amazing food and stuff. So it's a very livable place to be. Yeah, but all sounds good. I don't have any other questions. I think it would be great. You can end up in academia because, I think it's pretty rare. I have not really seen it from my department where at a defense, a student have 15 publications. I think that's a very, very strong indication of your future potential. And I would really love to see you to go places. So.
He's only surpassed by Anton, the guy below you on the Zoom call.
Really? Oh my God. Okay. Okay.
It doesn't really count my publications because it was like experimental work. You just simply need to put more hours. That's it. But Kai published everything with his brain, so that's why it is very important. I guess it's very impressive what Kai did.
Oh dear. Everyone here, we're all standing on the shoulders of everybody else. Yourself, Anton, Dr. Sparks. It's impressive, but it's everyone's efforts. I'm not going to try and claim I'm any more gifted than anyone. I'm just glad it's happened, and I appreciate hearing that, Ray.
Okay, I'm going to go ahead and create a breakout room real quick so we can have a deliberation. You have another question, Bae?
Yeah. I actually have one last comment, and we don't have to spend this time to do it. We are recently, this is actually, I think you and I chatted, Kai, you and I chatted quickly when you gave a talk at the data seminar a few years back. We were actually right now working on something that is interpreting BERT models. Where we kind of, of course, this is more on the NLP, not in the material science, but I kind of envision this could be applicable to CrabNet, for example, because it's based on some form of transformer. So what we did is that we're looking at the BERT network, and we're looking at activation vectors of the neurons at each layer of the BERT. And we focus on there's 12 layers for a particular BERT the BERT we have. So there's 12 layers, but we're looking at the activation vectors of the neurons during that, after training, and then you probe it with a bunch of sentences, and then you collect those activation vectors. And then we're looking at sort of how those activation vectors are grouped together, and use that as a way to interpret how this BERT model works. So it's more along the line of interpretability, but I feel like the same framework could be applicable for example, CrabNet, kind of explain why, for example, certain compounds are kind of considered similar from the perspective of the activations. So I feel like it might be an interesting potential future work to look at how to interpret how the CrabNet is behaving. So this is more of a comments, and I kind of partway through, I forgot this comment, but now it came back to me. So
yeah, I mean, I'd love to look at that kind of stuff. I've never really done too much probing network activations, but if your group has some people who are experts at it, it's the base implementation. So it'd be pretty easy for us to change composition. You know, I mean, just feed as much data as you want in, generate it.
Yeah, I mean, our framework has, we kind of moved from neural network to neural network. We did like Inception V1, which is a image classifier, and then ResNet, which is also image classifier. And then we moved to text classifier, which is BERT, and so on. So, I mean, it's pretty oblivious to which neural network we try to probe, but it's kind of occurred to me that if we want to add a little bit more interpretability to how CrabNet say behave in this way, this will add a little bit component to it, to how to interpret its behavior. So anyway, this, yeah.
I imagine it'd work well because our vocabulary is only about 90 different elements. So it should be easy.
Yeah, I will follow up. I mean, our paper's on archive, it's published and everything. So I will follow up with some references. But I know Taylor wants to get the official business now, where I think you will go to a wait room, right?
So I've just sent everybody an invite. So we will join the deliberation room. Kai will join the waiting deliberation room.